Hi everyone. I want to first apologize about my voice. I hope it's going to be okay. I had a cough for the last few days, and I think since this morning I have some trouble talking, but I hope I'm going to make it through. So yes, I'm going to be talking about visualization of high-dimensional data using the Tora package and combining that with Shiny and Plotly as well. And I want to start out by motivating why I want to extend Tora with Shiny and Plotly.
I will give you something better for your voice, okay. But I ask you to stand here.
Stand here, yes. Okay, thank you. Yeah. Thanks. Okay, so my background is actually in particle physics, and I'm going to be using an example from particle physics to show you why I wanted to have these new kind of features with the Tora package. And so what you can see here is kind of an example data that we're dealing with in particle physics. So this is what we call an event display from the CMS experiment. There's a lot of things going on. Just so you know, this is a single proton-proton collision that's been observed by an experiment at the LHC. I'm not going to explain everything, but I want to make the point that particle physics experiments are these really highly complex environments. And the way that we're trying to make sense of that is by using computational tools. So we're really heavily relying on things like simulations and global fits, which also means that we're in turn relying on visualization to understand what's actually happening. And one thing about particle physics is that we're usually relying on dimension reduction because what we're looking at are 1- or 2-dimensional plots, but usually our data is multivariate. And so I want to make this more concrete, but also take more of a data-centric view of the issue. And so I'm going to give you one example that I've been looking at. And the example is that we're trying to understand the nucleon structure. So for example, understanding what's going on inside the proton. And the way we're doing is by doing global fits in some high-dimensional parametric model. And what the PDF Sense collaboration actually tried to do is trying to understand how each single measurement that a particle physics experiment is making actually impacts the fit. So what's the sensitivity of the fit to each of the measurements? And what ended up happening is that they're defining what they call fit residuals in a high-dimensional parameter space, which is 56 dimensions that's characterizing the parameter space of the model. And then each entry, each observation would be one experimental measurement for which we want to analyze the sensitivity. And so we have this data problem where we have a data set in high dimensions, and we want to understand things like grouping and outliers. So the grouping in this case would tell us how different types of measurements constrain different directions in parameter space. And then outliers are really important here because what we're trying to understand is the sensitivity, and something that looks very different is essentially telling us that this is going to be important in constraining our fit compared to everything else, so compared to all the other data points that we have. And so obviously visualization is the best way of addressing these questions, and that's what we did in this physics paper as well. Gonna have to reload the page, I'm afraid. It was working before. Maybe I'll try a different browser. Sorry about that. Okay, I'm just gonna see if the next one did come out. Oh, sorry. Oh, I'm really sorry. I'm not sure how to go from there. Okay, so that's working at least. So we don't see it, but the first thing that I tried to do is to just reduce dimensionality using principal component analysis, which in this set, in this data set, it does allow us to see. So I was also splitting it up by different groups, and it did allow us to see a little bit the difference between the groups, but also to see kind of interesting structure. But what was the case here is that actually two principal components didn't capture a lot of the variation, and we would have to look at least at the first four principal components to get the full picture. And so this is a great case for using the Grand Tour. And so this is what you can see here, just using a Grand Tour animation with the Tour package. So you can see on the left the code to generate this visualization. Essentially, we're just calling the animate function. We're calling it with a Grand Tour path. So what that means is that we're randomly selecting bases between which we're interpolating. And then I also made some specifications about the display type. So I'm using a group display to really be able to compare different groups as well. And you can see the result on the right. So the first facet here is showing you the axis. So that's a representation of the current projection. And then we have the 7 different groups that I'm separating here. And this really allows us to compare the groups in detail, much more so than the principal component view, which you unfortunately didn't see. But one thing that I want to highlight here most of all is that this is a really neat way of seeing multivariate outliers, so of visually identifying multivariate outliers. And what I did in this work actually was to relate the multivariate outliers in the parameter space to some of the metadata that I had. And I then used marker symbols, so that's the PCH that I specified in my tour function, to highlight them on the plot as well. So maybe a few to point out, maybe the most extreme is the one here on this Atlas 7 new data set, which is marked by an asterisk. That is really clearly different from everything else in our distribution. And so when I did that, I really had to do a lot of back and forth to figure out how my metadata was relating to the things that I was seeing in this tour animation. And that got me thinking that, well, it would be much easier if I had some kind of interactivity here. So if I had tooltip information, or if I had a way of brushing points, I wouldn't have had to work so hard to figure out how my metadata relates to what I'm seeing in the display. And so that's what we went ahead and did. We tried to make an interactive interface to the tour package. So that's the Galab package, which is essentially a graphical interface to the Tour R. Let me start by talking a bit about the kind of the reasoning behind that. So I had two kind of different type of things that I wanted to accomplish with the package. So one is that I want something that's really easy to use. My main reasoning is that people in physics aren't really users of R. So I want to have all the major options available in the graphical interface. So we build in things like file upload, selecting between tour types, display types, also more advanced options like selecting projection pursuit index functions for a guided tour. But at the same time, I wanted to have all these features that I wanted to have. So these interactive features that I've already talked about, like linked brushing or tooltip information, also things like moving along the tour path, which is really nice for backtracking. So if I saw something and I want to go back to that particular plane in the sequence, that's something that I want to be able to do as well. And then again, there's more advanced options that we can think about, like starting a local tour around the current viewing plane. And so what we ended up doing is we take the Tour package and we're combining that with Shiny and Plotly to provide us with these interactive features. And I'm gonna reload that, so that's hopefully gonna work. Okay, so that's just a short demo of how the package looks like. We have separate input and output panels, and here I already loaded my data set. I select the parameters and the display type, and then I look at the results. So this is the same data set, but now I have the metadata as well on these 1D parameter plots on the right, and I'm using that to brush points in my tour display in the center. And what you can see is that by doing the selection on my metadata, I can highlight the points in the tour display, and once I start playing it, it will become clear that these regions in the metadata parameter space really relate to specific behavior in the tour display, so in the parameter space that I'm interested in. And so that's what you can see here. You can also see on the bottom I have what I call the timeline. So this is just showing in black where we are in the tour sequence, and in red are the anchor points. So everything else in between is just interpolation between basis planes. And what is really nice, we will see in a minute, is that I can use the timeline to actually go back to some of the planes that I've previously seen. So here I've seen some that are very useful for distinguishing these parameter points from the rest of the data points I have. And so if I had more time to spend on this, I would probably go back and start a local tour around this viewing plane to understand more about the structure in my data. I want to just take a minute to also talk a bit more about the different display types that we have here in the results panel. So I've already mentioned that on the right side we have these one-dimensional displays of all the parameter values. So these are actually all the numeric parameters that occur in the input data set. And I think that's really useful for this kind of linked brushing as we've seen in the example. Then the main display in the center is the tour display, which has the projected data points. In addition, it also has a projection of the hypercube. So this is a hypercube containing all the parameter points in the high-dimensional parameter space. And essentially, it can give us an idea of how empty the high-dimensional parameter space is. Then we also have on the left the axis display. So as we have seen before, this is just showing us the current projection, basically telling us what we're looking at the moment. And then finally, what is interesting on just below the axis display is what I would call a coverage display. So what we're trying to do here is to give the viewer a sense of how much we're covering the space of projections. So if I'm looking at a short sequence in a high-dimensional parameter space, probably I will not have seen a lot of the information because I only saw a small viewing angle in the total space of projections. And the way we're trying to see that here is by using principal component analysis on the space of the projection vectors. And then you can see in the space of the first two principal components all the projections that we've seen in green. And then in purple as well, we see some anchor points that are just making sure that we're really spanning the space in this case. Just to give you a little bit of technical detail, so the full code is available on my GitHub and you can have a look, but I want to give you a little bit of an idea of what is going on behind the scenes. So obviously, all these interactive and dynamic functionalities rely heavily on Shiny observers. And we couple that with Plotly event data and the Plotly proxy interface. And here I just have one example, which is how we're actually updating the plot for each new projection in the tour sequence. And so we're using the Plotly proxy interface and first grabbing the tour object from the Shiny session, and then using Plotly proxy invoke to restyle the x and y values for both traces in our Plotly object. And just to finish up, you're very welcome to try this yourself. We currently have the developed version public on GitHub. And it's really easy. Once you have it installed, you just call the launch app function and it will load with the default dataset. And you can then use either the file upload or you can launch it with your own dataset as well to look at your own data. There's a lot more information online on this webpage, which has a bunch of different examples to show off the different use cases. And once we finalize the last few things, hopefully soon it will be on CRAN as well. And that's all I wanted to say. Thanks for your attention.
Okay, that was great. Thanks, Ursula. So do we have questions? We have one back.
Hi, thank you for that presentation. So a quick question about the number of data points that you show on that plot. Is there a limit to how many it can render before it significantly slows down, or is that just a computer specification?
Yes, there's definitely a limit. So on my laptop, usually a couple thousand points would be okay, but not more than that. We're trying to use the Plotly to WebGL feature to speed things up, but there's still, like, we're re-rendering a lot of time, so there is strong limitation on how many points you can actually look at.
Okay, more questions? Yeah.
I didn't see where. Here.
Hi, great talk, thanks. I want to ask, did you consider using bokeh in order to visualize more dimensional data on a flatter scale?
No, sorry, I'm actually not aware of what that is. What was the name?
Bokeh is an R package.
Okay,
In order
I'll have to look into it.
okay, but
Okay, I think we have time for another one if we have one.
Hi. You showed 6 principal components. Do you select these 6 for some reason, or you can configure this in your package, or how do you select them?
Right, so the package is assuming that you already prepared your data. So in this case, I pre-selected the first 6 principal components to write in my data table. And then in the package, I think we can't really see the input panel, maybe if I reload. There's the option of selecting which parameters I actually want to be including in my tour. So in this case, I'm unselecting 2 of them, and I'm only looking at the first 4 principal components. So yeah, you have to do the first step, and then you can select which ones you want to actually include in the display.
All right, thank you very much.